tell how to make the ghost-free UV completion for Starobinsky inflation, probably and possibly working on energies up to infinite energies. This would require for this kind of framework dealing with non-local quantum field theory, and I will give a brief review on the recent results. Part of them were obtained by me and Alexei Koshelov on theoretical grounds for non-local scalar field theories, amplitudes, and what does it mean, how to define all quantities needed for building quantum field theory in the case when the theory appears to be non-local. Then I get back to gravity and present a normalizable ghost-free action, which would be a good opportunity for good option for the gravity theory, which is both simultaneously ghost-free and normalizable. And then in this kind of model, it was shown that the Starobinsky inflation is an exact solution. Surprisingly, the normal local solution would be an exact solution of some quite complicated non-local action. And I present the results where we computed gravitational wave production up to the observables in this kind of model. So let me briefly review what is Starobinsky model of inflation. It was actually the first model for the accelerated expansion of the early universe, presented by Alexei Starobinsky in the year 1980. Inflation is driven by a quadratic curvature correction to the gravity, and this model of inflation is still can be considered to be valid, and it survived with respect to all new Planck data because it predicts very low amount of tensor gravitational waves, tensor modes in this model, and it appears to be kind of still in the center of valid region, which is not excluded by Planck data. Unlike the many models like m² phi² inflation and the other power law models, as well as a lot of other different possibilities. Of course, it's very interesting to ask a question: what could be the completion of this model up to infinite energies? It's maybe too we require too much here, but still, it was known for years that if this section is actually, if one adds allows for the presence of y² in this section, then the gravity, the theory of gravity defined in this way would be renormalizable. So unlike the GR, it would be a renormalizable theory of gravity. But unfortunate thing in this theory is the presence of the ghost, like Leaf explicitly presented degree of freedom with the wrong sign of kinetic term, which is unavoidable, at least in kind of local models. But if we allow for the presence of non-locality in the action, the explicit presence of non-locality, then we allow for infinite number of derivatives in the Lagrangian, in this case, we can have a very interesting and promising option that the theory can be ghost-free. This theory in its generic form is presented here. It can be written like R, some function of the Lambertian operator R plus wild tensor converted with some scalar function of the Lambertian operator and the Wild tensor. Here I mean that the indices of Wild tensors are contracted one to each other. The study of and proof of the possibility that this could be also a normalizable gravity was done in the work by Terry Tomboulis, and checked after that in several papers. Of course, we need certain conditions on F and FW. In this case, ghost-free action require let's look at what are the conditions required if you want to keep the following spectrum of this theory. If you want to keep graviton in the spin-2 sector and scalar field in the sector of with zero helicity and no other degrees of freedom at all. From this section, one can compute after some kind of long procedure of computations, one can obtain this result that the propagator takes this form. And if we want to keep only a massless graviton in the helicity 2 spectrum of the theory, we require that the propagator of tensor modes should be of the form box multiplied by exponent of sigma of box. Sigma of box would be any entire function, and exponent of sigma of box in this case would be a function which doesn't have any zeros or singularities at all. So it's a function. So the simplest choice, it would be just an exponent, but it could be much more complicated. Then in the scalar sector, we get somewhat more complicated expression, and we require this to be of such a form that there is a massive degree of freedom, and also some exponent of sigma of box, which doesn't have any roots or singularities. And it's possible to construct this kind of function. But in order to make a good theory out of this, we must have a connection between one sigma of box, sigma and sigma 1 actually. Because if we derive from this expression what should be f of box, then we get this kind of mess. But since we do not want to have some problems in the IR or any singularities of this function in f of box explicitly standing in the Lagrangian, we require the cancellation of terms with box in denominator, and it's very easy to achieve if we require that this exponent is equal to 3. In this case, we have kind of very nice properties of all the theory. But it means that now f and fw of box are not independent functions, which were thought for a long time. But our recent finding is that these functions has to be connected. And this is exactly what should be the connection. F of box should be of that form, containing sigma of box, and fw is also depends on the same function sigma of box. And under these conditions, we have a good behavior of the theory and no ghosts in the spectrum at all. No, but the spectrum contains scalar field and graviton. Massless graviton. So, in order to make theory of gravity ghost-free and probably renormalizable at the same time, we have to go for infinite derivative actions containing infinite derivatives. What is the status of such kind of theories from the point of view of quantum field theory? They have a very good benefit that the loop integrals could be made convergent due to the suppressed propagator at large momenta. Actually, if we have the scalar field with or graviton with form factor f of box, it turns out to be that the propagator takes exactly this form, and if we take the function f of k squared falling down at large k, we can easily achieve the convergence of loops. Historically, such models were considered as a way to avoid loop divergences, and up to my knowledge, the first attempts to build such kind of theories were done by Kuzmin, Efimov, Krasnikov, and there were several papers of that. And besides that, the theories with the infinite number of derivatives appear very naturally in field theories derived from the string field theory. If string field theory if one takes the kind of field theory limit, then it appears to be non-local field theory, which was studied by Witten, Sen. Non-local operators are also good for could be a solution for building a possible UV completion for gravity. But let me turn to the scalar field example, because gravity is very complicated theory, but scalar field is much simpler. And even from the point of view of effective field theory, it could be kind of natural to have infinite number of derivatives in the action, because actually once the scalar field is non-renormalizable, so once we have 5 to the 6 term in the potential, it means that loop corrections generate all possible terms which are not forbidden by symmetries. And most likely the number of these terms would contain up to infinite derivatives, up to infinite number and infinite derivative terms. And then one may ask a question, all possible terms, are there any classes of good theories in this kind of mess? Probably some, there are some classes of theories which where all these higher derivative terms can be converted in such a nice way that the whole theory becomes renormalizable. And it's very easy to build up such an example in the framework of just non-local scalar field theory with any potential. And if we write down this kind of non-local function with a proper behavior at large momenta for the propagator, then it would mean that this theory appears to be UV-finite for any potential of E of phi. And in my recent work in collaboration with Alexei Koshelev, we applied this technique for healing of the Higgs inflation model, which is known to suffer from low cutoff scale, which makes it hard to describe inflation and especially reheating. And we have shown that this model is more or less easily improved with the introduction of non-locality to UV-finite theory. And this is the correction to the Higgs potential in this case. And it can be done in such a way that Higgs inflation is not affected by this correction. Most likely, only the intermediate region is affected. So for non-local scalar field, with even this simple model, we get a UV-finite theory, especially with the potential phi to the 4. It's very easy to study what happens in this kind of theory and how to define properly the amplitudes. And also how to compute amplitudes. Surprisingly, this series looks like very complicated, but surprisingly, it is possible to get even some analytic result computing something in this series. In order to get a good theory, we should have the form factor f of box here, such that it doesn't have zeros and poles on the whole complex plane, which means that it should be an exponent of entire function. To make loop integrals convergent, it should fall faster than 1 over q to the 4 for negative q squared, which actually in Euclidean domain. And the residue should be 1 in this series. Then let me turn to the maybe main complaint about non-local series, which I heard many times, which is a feature of weak rotation in this case. Actually, the amplitude defined, it's a bit tricky to define the amplitudes in Minkowski space in this case, because if one writes this kind of integral in Minkowski, it appears to be just infinite. Euclidean integral is okay and it's finite, but then it's hard to understand what is the connection between Euclidean and Minkowski amplitudes in this case. So this connection is more tricky because weak rotation cannot be done because the contour integral here appears to be infinite, and there is no, it is not possible to choose the form factor in such a way that this infinite contour will give some sensible result. So in any way, non-local series and amplitudes of non-local series in Minkowski space, naively written in Minkowski space, appears to be just divergent. But there is a proper way of defining of the amplitude in Minkowski space. It should be, the recipe is that we should write down this amplitude in Euclidean for Euclidean momenta, and then accurately analytically continue it to Minkowski external momenta. One of the main results on the way of understanding why it is a proper way was given by Ashok Sen for actually string field theory amplitudes. And this generic result says that if the amplitude is defined in such a way, then we obtain that these amplitudes are unitary. So optical theory works in this case very well. And we explicitly check this in our work. Just for a Fisher diagram, it can be computed explicitly. For computing this amplitude, it means that we should do everything actually as in local theory, just forgetting about the fact that it's the both Minkowski integral and large and infinite arc are just formal expressions, but Euclidean integral is gives some sensible answer. And in this simple case, imaginary part of the amplitude appears to be the same as it happens to be in local theory. What happens here is that there are two poles which are touched in this computation of one loop diagram. And we must not forget that to add to the amplitude also, not just take the Euclidean answer, but add the residues in these poles. The residues in these poles contain imaginary part of the amplitude. Actually, it's a real part of this I pole. And also some contribution to real part of the amplitude. So it's very essential to have this kind of contribution of the poles, especially because regardless of the form factor, this contribution appears to be the leading contribution. And let me show this explicit result for the amplitudes. If f of box is exponential of box, then one can compute, one can do all these integrals, perform all the computations, and obtain that the matrix element has this form. It can be done through the analytic expression in terms of in terms of special functions. as well, it has the matrix element has imaginary part as it should be in the local theory, or as it should be consistent with the optical theorem in non-local theory. And this is how m depends on momentum p squared. Of course, in the limit of small momenta, we have logarithmic divergence, which corresponds to the behavior of which reproduces actually the fact that if non-locality scale goes to infinity, then we reproduce local normal divergences in local theory, logarithmic divergences. And at large momenta, this amplitude is growing, which means that most likely at infinite momenta, the theory goes into strong coupling. But for other form factors, it can be possible to construct such form factors where the amplitude doesn't grow with momentum, and the theory is likely in the perturbative regime even at infinite momentum. So let's now turn to gravity and see whether all that knowledge can be applied for building the gravity theory. So if we require for the theory of gravity be probably renormalizable and ghost-free at the same time, then there is no way except non-local infinite derivative theories. Of course, if you are working in 4 dimensions and are not dealing with some kind of string frameworks, it's about just quantum field theory. It's another option for what could be the theory of gravity. Power counting arguments imply that if the propagator falls down fast enough, then all loop diagrams containing more than 2 loops in gravity are converged. But one loop divergences are still there. However, they are local and have the same form as in GR. This happens because form factors now are present both in propagator and in vertices, and they cancel each other at the level of 1, which means actually that one loop divergences are the same as in general relativity. But at one loop, they can be cancelled by just adding local counter terms. The propagator can be decaying as a power law of momentum for both real and Euclidean momentum. This is an issue which we need in order to have both some sensible amplitudes at tree level and convergent loop amplitudes. We need a function which, so in gravity, it's not good to have a form factor which falls down exponentially. It's better to have form factors which are falling down like power law. And surprisingly, as a mathematical result, it's possible to construct these functions, and they are not crazily complicated. It's one of the examples is presented here on the plot, and actually it is a gamma. It is an incomplete gamma function where we just incomplete gamma function minus logarithm. It appears to be a good function which falls here as 1 over k to 4. And this is modulus of this function on this plot, where we can see that still there should be some directions at the complex plane where this function grows. And it's impossible to avoid this issue, the issue of essential singularity at infinite momenta at the complex plane. It is also the typical issue which appears in non-local gravity. This would invalidate all possible dispersive relations which are normally used and thought to be valid in local theories, but still, up to my knowledge, it doesn't invalidate the theory at all. Like, it doesn't mean that the theory is really bad if it contains some amplitudes or propagators which in some complex directions, in some really unphysical directions, is growing like exponentially or maybe even faster. So another result about non-local quantum theories is that amplitudes have the same analytic properties as in local theories, except this essential singularity. It was shown in the works by Terry Tobulis in the 90s. Actually, it means that most likely there are no problems with causality in the theory and the theories. No some unexpected poles or singularities. Let me turn back to the Starobinsky model. Infinite derivative gravity could be, in this sense, a good UV completion for the Starobinsky model due to the following surprising result. The local Starobinsky inflation, where this is an equation of motion, local Starobinsky inflation, this equation, this ansatz goes through all the quite complicated equations of non-local Starobinsky model, of non-local gravity. And it remains as exact solution under just one condition on this function sigma at the mass of scalar degree of freedom and should go to 0. It doesn't contradict to something in this theory. Then, due to that fact, one can consider infinite derivative gravity as a UV completion for Starobinsky model, and there was a lot of work done in
Anna, we seem to, we lost you. Can you say something?
Seems to have disconnected. Anna, can you hear us? Apparently not. There seems to be a bad connection. Ah, there you are. Can you hear us?
Or maybe you can send WhatsApp or something. Prefer.
Yeah.
Yeah, I just let her know.
Oh, okay.
Yeah, she's obviously trying to fix it.
So sorry, I was muted. So yeah, we so okay, I need to make you a co-host again, I guess. No, you must be able to share, and
Yeah, that's good.
you can unmute yourself. Can you try to say something? Okay, first maybe share the screen.
Can you hear me now?
Yes,
we can hear you. That's fine.
Okay, that's great. I'm really sorry. I experienced some interruptions in internet connection at Imperial College. I don't know why it happens.
Oh dear.
So I stopped at the explanation of why infinite derivative gravity could be a UV completion for the Starobinsky model. And in this direction, there was a lot of work, and it was shown that if the scale of non-locality, which actually is suppressing box powers in the form factors, is larger than the mass of scalaron, then this model is very similar to the Starobinsky inflation with some small corrections, which could help to find out from the observables what could be the bounds on non-locality scale. The presence of non-local terms can just slightly change the predictions, but there is another issue connected to the higher infinite derivative theories on top of non-trivial classical backgrounds. And this issue is not well studied yet. There could be some classical instabilities corresponding to the appearance of ghosts on top of non-trivial backgrounds, but we have a showcase at hand that in the scalar field theory, actually in non-local Higgs inflation, this issue can be resolved by the special choice of non-local form factors. So we have hope that in the case of gravity, this issue also can be resolved, and the Starobinsky solution can be proven to be stable in this case. Another issue is connected to the previous issue, is that we might have overproduction of gravitons after inflation. In Starobinsky inflation, there is no significant graviton production due to the rolling inflaton field and the subsequent oscillations of the inflaton. But if we have some higher derivative modification, then we might get production of gravitons. And this is exactly the question which we have been studied in the work to appear soon. We prove that graviton production is actually determined only by the term while box while in this non-local gravity, regardless of the presence of higher derivatives and higher terms. And this happens just because of on-shell condition on the graviton field, that graviton is actually massless. This means that only one term among infinite number of them is responsible for production of gravitons. So we can consider a toy Lagrangian for graviton production, where here the only relevant terms responsible for graviton production in actually any generic model of containing higher derivative terms of gravity. So it could be also valid for just effective field theory of gravity. We try to be as much generic as possible. So we keep this RY squared term and compute the decay width of the scalar degree of freedom to gravitons. We obtain this result where we have a quite large power of suppression, scalar on mass over non-locality scale, the power 8, and connecting to the observables, we can compute how much gravitons which are produced after inflation could be a dark radiation, and they will be contributing to the number of effective neutrinos at the later stages, and this is quite strongly constrained. So we can obtain the number out of these computations and get a kind of generic bound on the non-locality scale or on the scale of suppression of actually quantum gravity operators. It should be larger than 3 scales of inflation.
Anna, you've had half an hour?
Okay, I'm finishing already. It's one of the last slides. So besides that, we also computed the gravitational wave signal from the decay of inflaton, but it is from the point of view of constraints or potential observations, is less interesting because the prediction is that the signal would be quite low, even in the case if this is for the decay width to gravitons over decay width to standard model particles being 10 to minus 3. And still the numbers are very low because the lowest characteristic strain for gravitational wave signal, which is available for very far future gravitational wave detectors, is 10 to minus 24, which is far away from what we predict here. So even a little bit surprising fact here is that even the universe would be dominated by gravitons after the reheating. So if the inflaton would decay to gravitons, mostly, then even in this case, the signal would be quite low. But of course, we get some other problems in this case, which rule it out. So let me come to conclusions. Non-locality can make non-renormalizable theories renormalizable or even finite, which is a good advantage of and kind of in the attempt of getting renormalizable theory for gravity. The Minkowski amplitudes can be defined as analytic continuation of Euclidean amplitudes, and this has been proved to lead to a unitary theory. So it seems that non-local quantum field theories are not bad if the amplitudes are defined in a proper way. At least there is no kind of no-go theorem why it could not be an option for quantum field theory. It is possible to construct a ghost-free theory of gravity, keeping renormalizability at the same time. But of course, here we have to deal with the infinite number of derivatives. It is a very complicated theory, but surprisingly, a local solution of the R-squared inflation appeared to remain as an exact solution of non-local gravity. Higher derivatives in this kind of theories do not lead to overproduction of gravitons after inflation if non-locality scale is high enough. The bound is quite weak, and the same bound of the bound of the same strength would come also from the other considerations, like requirement that other observables have to be consistent with the Planck data. The strongest bound for gravitational wave production comes from effective number of degrees of freedom, while the gravitational wave signal appears to be negligible. This happens actually due to the fact that the energies of produced gravitons are quite high, and they correspond to high frequency gravitational waves, which are very hard to detect. And this is the same situation. This fact is quite generic if one can consider the production of gravitons by decay of inflaton field. If inflaton field decays to gravitons, then it cannot give a large amount of large gravitational wave signal. The same happens for all models where we can make inflaton decay to gravitons, regardless of the nature of the scalar or the interaction between scalar and gravitons. Thank you very much for your attention.
Thank you. Thank you very much. Are there any questions for Anna? Andre has a question.
Yeah, thanks for the nice talk. So about this overproduction of gravitons due to non-locality. So is it generically good or bad for preheating, in the sense that can it, for example, assist gravitational production of dark matter, which then freezes in?
What do you mean by gravitational production of dark matter?
Well, for example, when you have a process like two inflatons, for example, they produce dark matter via graviton exchange, and the dark matter in this case can couple only gravitationally, and still it is produced. So, can you imagine some type of process also taking place in your theory?
In principle, it can happen, like even if local Starobinsky model, non-locality doesn't matter actually at this stage already. The process of the form that scalar field, inflaton field decays to fermions is quite natural to arrange, because if the fermions are heavy enough, then they are coupled to scalar field, to R-squared scalar degree of freedom, and they could give a contribution to dark matter. I think that was exactly what was considered by the work by Dima Gorgonov and Alexander Panin.
Okay, but this is without non-locality. So can non-locality somehow enhance this,
It would
or
not.
give?
It should not enhance because non-locality scale is higher than inflationary scale. It should be higher because otherwise we could spoil inflation and predictions. So it should not change the result a lot.
So this additional gravitons, they really contribute just to dark radiation, as you said.
Yes, yes.
Thanks.
Thank you. Valerie is next.
Yeah, non-locality is non-locality. How will it show up in physics? Is it going to be a causal behavior? What are the scales of causality? What is the new features in the physical sense?
The question of the issue of causality is something actually to be that should be better studied in the series. It's kind of for future work, but from the point of view of physics, since the non-locality scale here is assumed to be quite high, we should not see any effect of like in particle physics at all.
Well, I can imagine you can proliferate if you are in Minkowski domain. Then once you are non-local somewhere, then you're going to be non-local everywhere at certain time later on. Don't you think so? Don't you think so?
You mean that kind of if there is some a causality in small time?
It would increase. You have
Yeah, it would
sort of you're going beyond the light cone, so and the light cone expands, so you're further and further out from the light cone.
Well, this is a good question actually. How non-locality could sum up when you go from small scales where it could be or a causality to larger scale. It's an but I think that the same happens also in some higher derivative theories, just even in local theories, and it doesn't invalidate the theories at all.
Also, let me just mention that in principle, it is possible that micro causality violation doesn't lead to violation of causality at macroscopic level. So kind of, it is possible to confine it at microscopic level.
Yeah, that's my point actually. But in these concrete theories, I think it's a question which would be just a matter of computations. What should be the time advance in this kind of solutions? Another physical matter here could be connected to black holes. There are some claims in the literature that in non-local gravity, black holes could be there could be non-singular solutions. So it could look like a black hole from far away, but be still non-singular.
Okay, are there any other questions? If not, I think let's thank Anna for a nice talk. And apologies for your connection problems. And
I apologize again, sorry.
no, not your fault.
Okay.
And thank you very much. So let's pass on to the next talk, which is by Vladimir Belokurov. I don't see you. Are you connected, Vladimir?
Well, okay.
There you are. Good.
Let me see. Well, I don't know. Here is the name of my grandson, Timothy. I don't know why. Well, okay.
Okay, so I need to make you co-host. Okay, I see. So, but then we also had some echo. Maybe me see what I need to do.
Okay, well,
Yeah, yeah.
sorry.
We're having some echoes.
He is in two instances on Zoom.
Yeah, maybe if I
that's why-
mute one of them. Can you say something? Okay, maybe it was too.
Maybe it was.
Okay. Now both of them. Just a second.
Well, I feel that's okay.
Yeah, it looks to me that Anna is not muted. So
Is it okay?
No, but Vladimir, which account I used?
Inar, it seems to me that Anna is not muted. Can you mute her? Wait.
Let me see.
Well, I feel it will be better. Do you hear me? Excuse me.
Yes.
Yes, we can hear you.
Okay, perfect.
But still, there is some noise.
There's still background noise. Maybe everybody who's not speaking, if you could mute. And then, yes, so Vladimir is going to tell us about path integrals in 2D and 4D quadratic gravity models.
Okay, and first, let me express my deep gratitude to the organizers of this significant workshop. And I think that they did a lot, not only for joining the people working in this field, but also they made an experiment in constructing a collective mind. Maybe it would be some first steps in this field also. Well, my talk.
Vladimir, we can't see you. Do you want to switch your camera on?
No, well, I switch it because, well, I use two computers. Well, and
okay.
yeah.
All right, no problem. It's just,
maybe, well,
just nice to see the speaker, but no problem if it's difficult.
Well, my talk, well, is based on our papers with my colleague Evgeny Shevgulidze, and I would speak about our first small steps in a very ambitious program constructing a solid mathematically rigorous basis for calculations in quantum gravity. Let me start with some introductory comments. Well, you see, all of us were spoiled by the common situation in mechanics and general physics, where the action, well, is the integral of the difference of kinetic energy and potential energy. And we consider the measure of path integrals that we would like to write in quantum mechanics as the integrals given by a free action, which is integral of kinetic energy. First derivative of dynamical variable squared, not the integral, in the integrand. In particular, in quantum mechanics, in simple models of quantum mechanics, in imaginary time, it is the Wiener measure. Well, we know how to calculate these integrals, and in quantum field theory, we have the same situation for common models of fundamental interactions. And we maybe that inside of us, there is something that tells us to use the Wiener integrals, well, and try to reduce all the problems to Wiener integrals. However, we have some examples where the action is not the simple, has not simple, so simple form as I told before. Well, the very well-known examples are SYK model and Jekyll-Teitelbaum-Dilaton gravity. These models lead to an effective theory with the so-called Schwarzschild action. Action contains the Schwarzschild derivative in the integrand. And let me pay attention on the sign, minus sign, before the integral. The dynamical variable has the sense of diffeomorphism, well, say of the interval, of the unit interval, or the positive semi-axis, or maybe a unit circle. And what is the first desire? The first desire is to consider the second term. No, let me try to the second term here as the term where the Wiener measure can be based. But the problem is the sign. Here we have the wrong sign, and so this way we cannot construct the Wiener measure. Well, sorry. In several papers, we proved that the correct measure, having the all needed properties of the measure, functional measure for integration, for path integrals, has the form mu d phi, and contains the integral of Schwarzschild derivative in the integral in exponent. This measure is a quasi-invariant. That means that it doesn't change the form under the action of the diffeomorphisms, as the Wiener measure does. And we derived the general rules of functional integration in the theories of this type. The idea of this method is based on some special substitution of variables. Namely, if we consider a continuous function on the interval xi, and then under the following substitutions, we can prove that the measure mu on the group of diffeomorphisms turns into the Wiener measure on the space of continuous functions on this interval. And there is the equality of functional integrals. This way we can calculate the functional integrals, path integrals with functional measure Schwarzschild, functional measure, reducing these integrals to Wiener integrals. So the experience we gained from this lesson is the following: that we have the true dynamical variable that define path integral measure, and we would try to find the substitution that transforms the measure into the Wigner one. We try to follow this guideline in the models of quantum gravity. First, we consider special model of 4-dimensional gravity. We consider the action that is contains curvature squared term, and find the dynamical variable that is invariant under the transformations of the space-time. Namely, we consider some reduced case. I will speak a little bit later. And we consider path integrals that are not integrals over the space of metrics, but over the space of continuous functions. Well, actually, these functions are related to conformal factor of the metric. And we consider these functions G, not G capital, that is metric, but G on T as the true dynamical variable. And the second our novelty is to treat path integrals as integrals not as the integrals over the functional measure that contains only the path of action quadratic in curvature. And the rest part of the action in the exponent stands in the integrand as the interaction term. We prove the measure mu to be equivalent to the Wiener measure, and made some simple calculations with in this method. This is the idea, and let me demonstrate how what is the realization of this idea. Namely, we study the gravity model with the following action, containing the lambda term, Einstein-Gilbert action term, and the squared action term. And we consider it in Friedmann-Lemaitre-Robertson-Walker metric, reducing actually the problem to the one-dimensional problem, because there is only only one variable t, time variable, time coordinate, and reduce the general coordinate invariance of the action to the invariance under the group of reparametrization of the time coordinate. We suppose these transformations be the diffeomorphisms of the real semi-axis, including 0 point. We know that the two coordinate systems are the most popular. They are so-called cosmological coordinate system, where lapse equals to 1, and conformal coordinate system where lapse and scale factor are equal. Well, and we distinguish the name of this variable t for cosmological time and tau for conformal time. Now we define the action of the group of diffeomorphisms on the functions n and a as follows. It is convenient to use other functions f and h instead of lapse and scale factors. Well, f and h are connected with n and a by the following equation. Well, the transformation rules for these functions are rather simple. Phi acting on f is simply composition of the function phi and f. And phi acting on h is also a composition, but a composition, well, h as phi, the inverse phi. Well, and now we can organize the functions g on tau. That is the composition h on f at tau. It can be easily proven that this function is invariant under the group of diffeomorphisms. It has a very transparent physical sense. This function turns the conformal coordinate system time to the cosmological one. Here. So the space-time metric is written in this in conformal coordinate system and cosmological system is written by the following equations. Okay. Now the invariance of the action manifests itself in its dependence only on the invariant functions g only. It can be checked explicitly, and we obtain the explicit form of all the terms in the action. Therefore, every four-dimensional space-time, and so the corresponding space-time FL or RW metric, is determined by its proper function g, and vice versa. Every function g determines the particular four-dimensional space-time. Thus, averaging over the set of functions g means the averaging over the set of possible four-dimensional spaces. That is, we have found the true dynamical variable. Now we consider path integrals in the theory. We consider them as the integrals of the form over the functional measure containing only the A2 part, the quadratic in curvature part, that has the following form. Oh, you can say, okay, this is very, very similar to something that is in the Wiener measure. Some derivative squared. Really it is, if we substitute q tau as the following ratio, we can write the integral in the exponent in the measured density in the form that it is needed for Wiener measure. Here, pi is p is connected. Sorry, p is connected with q by the nonlinear, non-local substitution. Well, it is not a non-trivial step, and it will be very convenient for us. But first, I'd like to mention that we have the one-to-one correspondence between the functions g and the functions and the Wiener variable p. And the measure mu written in terms of p is simply the Wiener measure. Now we can calculate path integrals over the measure mu, but there is a very important notion I'd like. You see, if we consider two spaces, the space of the path p and the path q, and we for p we consider the continuous functions, the set of continuous functions. The path q may have singularities of the form of the simple poles. It gives us the possibility to study the quantum correction to the classical solution of the following form. For this G classical, the solutions, you can see that you have the pole for the function q at tau equals to 0. So at the 0, we have q at 0 is infinity. And for this classical solution, we can consider it describes the inverse, the universe arising from a point and expanding. This is a scale factor, expanding with the slowdown as the square root of t. Now we would like to calculate the quantum corrections to the scale factor. Now we will calculate the path integrals in perturbation theory, and we consider the first non-trivial order proportional to lambda, the inverse lambda squared. Let me remind that lambda squared is the charge in the A2. Now we consider the corrections in this perturbative order. Well, it is this path integral. We have the inputs from all the terms of the action. And we obtain the result for the average scale factor as the function of cosmological time t. We have, surely it is the correction to the classical scale factor, square root. But in the first order term, we have other dependence on the time t. Let me remind that it is the first order correction, and the following orders give the well, the biggest powers of T, and we can do the perturbation theory this way. Now, the last part of my talk is divided to the path integrals in two-dimensional quadratic gravity. Here we also consider two terms in the action. K is the Gaussian curvature connected with the metric by known way, and the metric of the surface is written in the conformal gauge that we restrict the action to the conformal gauge. Well, it is the square root of metric G standing in the action. Also, as the action is invariant under the complex analytic substitutions, we can reduce the region of integration to the unit disk. Namely, we consider the specific form of the action of the following form. Well, here we have all three terms of the action, but with specific coefficients. So we can transform by the following substitution, where Q is the square root of G, and so reduce the action to the form of something, some derivatives squared. So it is the Euclidean path integrals can be written over the Gaussian functional measure. Gaussian functions. But we are to construct the method to calculate the integrals. And we will reduce this functional measure to Wiener measures. But first, let me say, if we consider the equation of motion given by this section, and we'll find solutions of the equation of motion, we reduce ourselves to the Poincare model of the Lobachevsky plane, and thus we should choose the boundary condition Q0 on the boundary of the disk, unit disk, is equal to 0. It means that the metric tends to infinity at the boundary. And the unique solution of this equation of motion is simply Q0. Well, we can rewrite the action making the following substitution. Instead of the variable psi, we introduce the variable f, and we see that the integrand in the action, well, is the Casimir operator of the group SL2R squared, and the integration here is over the measure is the integration over the measure that is invariant under the action of the group SL2R in the disk. Therefore, we obtain the SL2R invariant Gaussian functional measure. Well, how to reduce this SL2R invariant Gaussian functional measure to Wiener measures? We reduce this measure actually to the infinite products of Wiener integrals. The idea, if we consider the Fourier series of the integrand and write the action as the series, and then we have the relation between the variables psi and f above. Then we can express the terms in the action in terms of the coefficients of the Fourier series for the function f. Well, after some cumbersome substitution, well, written, I will not explain how we guess about these substitutions. We can transform all the terms in the action to the form which is well convenient to product the Wiener measure. And now our SL2R invariant measure on mu lambda df, well, is the infinite product of the Wiener measures. For path integrals depending on some on the modes with the definite numbers, the product, well, is reduced because of the cancellation of the same terms in the numerator and the normalizing factor in the measure. And so SL2R invariance simplifies the calculations of these integrals over the measure mu. In particular, the average function g square of the metric, well, is simply given by the classical solution of the equation. Well, and as an example, we have calculated the correlation function of the metric given by the integral in the first non-trivial perturbative order. First, due to the SL2R invariance, we can rewrite the correlation function depending on two arguments functions to the correlation function between the g at the center of the disk 0 and some point that obtained as the result of the shift at the Lobachevsky plane of coordinates, first and second coordinate. The first coordinate we transform shift to 0, and the second coordinate shifts to the following value. Well, and I am very close to the finish of my talk. I give here the result. We here have the classical solution and the corrections of the first order. Well, now let me finish with the following remark. Traditionally, and it is a common approach to struggle with the problems of renormalizability of gravity is to increase the number of derivatives, or even the introducing non-locality, as it is for the case of the infinite number of derivatives. This approach brings another problem, the problem of Gauss. Here we proposed the idea of some alternative approach. We suppose that the metric is commonly considered as a dynamical variable. It is not the dynamical variable. We would like to find what is a dynamical variable and to use the path integrals for the based on these dynamical variables. We consider our studies as a small step to construct a solid mathematically rigorous basis for calculations in quantum gravity, and hope that it will open new opportunities to construct this mathematically rigorous apparatus in theoretical cosmology. Thank you very much for attention.
Thank you. Are there any questions for Vladimir? I had a question, actually. It wasn't quite clear to me how you decided on the measure. What criteria were you actually applying to determine the measure?
Well, it should have all the properties of the. It should be a countably additive measure. Well, as it Wiener measure, the Wiener measure has.
Yes. I wanted to know to what extent the measure is unique. Let me put it that way. There's a long debate in the literature about whether the functional measure is unique. Should it be corrected?
Well, I'm afraid I cannot answer your question. So
Okay.
I know the papers that that use the Minkowskian path integrals. Well, but they are not absolutely convergent, and so they have some mathematical also some questions.
Oh yes.
Here, yeah. Well, so I knew the papers and yours.
Yes. No, it's really more a question of whether you. So let me phrase the problem a bit differently. It's well known in a theory like gravity that the Hamiltonian has ordering problems. There are P's and Q, momenta and coordinates,
yes.
multiplied together. And this is related to the fact that in the functional measure, this is not entirely unique. And so I just wondered if you had any thoughts. I mean, I understand your point about integrating over diffeomorphism invariant variables, but even so, is the functional measure unique, determined by symmetry principles, or is there some arbitrariness?
Well, it's a problem. Well, I have said that. Well, we understand the question, the problem, but we don't know the answer.
Okay,
so
no, that's fine.
Well, it is a good task, is a good problem for further studies. Yeah,
absolutely. Thank you.
Yeah.
Any other questions, comments?
Yeah. Neil, just a remark about functional measure. I mean,
Yes.
you have a freedom, right, to put something in measure or put something in the action.
Correct.
It's combination of the two.
Well,
So I can
yes.
say that
But-
I selected the
Excuse
measure
me,
in this unique way,
I don't see.
and then they change the action, right?
Yes. Yes, exactly. So that's what I was getting at.
Yeah.
So you chose a measure which would, according to which the action would give you the Wiener measure, right?
Yeah.
That was your kind of guiding principle, right?
Yeah.
You wanted to get the Wiener measure.
Well, because it is the only measure we can integrals we can calculate over.
Right. Okay, good. Thank you. I think if there are no other questions, then no other points anybody wants to make urgently, then I should just thank all the speakers for keeping to time and giving such clear talks. And let's thank Vladimir in particular. We haven't thanked him. And
Thank you.
Thank you very much.
much.
Thank you very much for joining us.
And for very kind atmosphere.
Okay. No, it's a pleasure. And I guess we are done for today. Is that correct?
Yes.
So maybe
Yes.
Also, let's thank Neil for chairing the session.
no problem.
Yes, thank you very much. So we can leave the room open if somebody wants to discuss. We can leave it open for some time.
But otherwise, we meet tomorrow, right? At 10:20.
Yes,
Yes.
see you tomorrow at 10.
10:20 Central European time.
10:20.
10:20.
Great. Okay, thank you very much.
Thank you.
Okay.
Bye.
Bye.
Okay. Bye, everyone.
Bye. So
So we need to, yeah.
I don't see anyone in breakout rooms. I don't know. Maybe we can close. We can wait for a few more minutes, in principle.
And we, organizing committee, do we need to discuss anything before?
Yeah, maybe
Oh,
since we're here, then maybe let's go.
Yeah, let's go to breakout room 1 then.
Okay. Mhm.